All right. In the last section, we discussed the first derivative test. What did it tell us? Exactly. So the first, it tells us more than that, actually. What else does it tell us? Very good. What are critical points or critical values? No. Zeros are x-intercepts. This doesn't tell us x-intercepts. Ah, yes. So what is an extrema? What does extrema mean? Make it more basic. Make it more basic. Oh yeah, yeah, it is. But I'm excited. What is an extrema? What's another easy way you can describe extrema? Yeah, the highest or the max or the lowest, which is called the min. Those are the extrema, the highest and lowest points of a curve. How do we find those? Yeah, the first derivative of x, f of x, is zero because it has no slope. It's a horizontal slope. So the first derivative also tells us the region or the domain where the curve increases or the first derivative is positive, and where it decreases. The first derivative is negative. Because that helps us now. We know a better idea what the graph looks like. We can first tell what the graph's going to look like by looking at the leading term. It'll tell us the end behavior of the function. Where the end of the graph going? Is it positive? If the leading term is positive, it opens up. If it's negative, it opens down. We can tell the y-intercept. This is all by looking at the equation, doing zero math. Then when we do the extrema points, whether it's increasing or decreasing, that's when we do the first derivative. Now, in this section, of concavity. Now, we discussed the concept of concavity. Concavity means what? In plain English, it simply means the bend of the curve. We have two types. We have concave up and we have concave down. That's what they'll look like. Think of a bowl. If the bowl is held upright, that's concave up. If it's upside down, it's concave down. So if it's concave up, then what do we know? The end result is if it's concave up, that means it's an increasing function on the domain. Why? Because as the graph goes on, the right side goes up. If it's concave down, is decreasing on the domain I. Because as it goes further to the right, it eventually goes down forever and ever and ever. Note, if it is concave up, we can say that it is convex. So that's whenever you hear the word convex, that's all it means is it's increasing function going up. So the first derivative tells us the shape of the curve, the direction of the slope. Concavity is defined by the second derivative. The second derivative test for concavity. Okay, why do I have to specify in parentheses that it's for concavity? What else is the second derivative used for? Think of application problems we've done already. Yes, very good. Acceleration. The second derivative of a position function is the acceleration of that function. First derivative is the velocity, second derivative is the acceleration. So we can't say second derivative test because we have multiple reasons for it. So now we're saying that it's for concavity. Let f of x be any continuous function that is twice differentiable on I. What does that mean, twice differentiable? Yeah, well, it has to have it to be twice, it has to have a second derivative. Give me an example of a function that only has one derivative. Nope. If it has an exponent, if the variable has an exponent, it's automatically at least differentiable once and twice. Linear, exactly. So if we had not really just linear, but we had a constant function. Because the first derivative of a constant function is what? You can't take a derivative, next derivative. So it has to be twice derivative, twice differentiable. Example 1. Find the intervals where the following functions have concavity. Find the intervals where it has concavity. In other words, tell me where it's concave up and concave down. So what test do we use for concavity? The second derivative. So for both of these, we got to take second derivative. The first derivative is going to give us 3x squared. Then we do it again. The second derivative will give us 6x. So where is it concave up? Where is it concave down? Remember, how do you know if it's concave up or concave down? What does concave up mean? When this f double prime, well, f prime increases, but what happens with f double prime? If f prime increases and you take the next derivative, what should that value be? No, it's going to be concavity. It's going to tell us concavity, but what should the value be? Is it going to be positive, negative, or zero? Positive, yes. So the first thing I always start off is, where is it zero? So we set the first thing we do, we set this equal to 0. Because that's where it's neither increasing nor decreasing. So we have 6x equals 0 at x equals 0. So now we know that our graph, if it's negative, if x is less than 0, what's my second derivative going to tell me? Right. Because since my second derivative is 6x, if I put in a negative number, it's negative. So the second derivative is negative. So therefore, well, the increase and decreasing is the first derivative test. But this tells us is that it's concave down. Since this is negative, it's concave down. Remember, increasing and decreasing is only first derivative. The second derivative defines concavity. Since to the left of 0, if I plug that into my function at the second derivative, it goes negative, so it's concave down. Now, for all my x's greater than 0, remember, I'm using the second derivative. If I only put positive x's in there, then my second derivative will be greater than 0. So it's concave up. It's positive. And we know that because what's the graph of the cubic function look like? That's x cubed. So anything to the left of 0, it's concave down. It's concave down. Anything to the right of 0, it's concave up. We'll come back to this point in a second. All right, let's look at the next one. Y equals x squared. My first derivative gives me 2x. My second derivative gives me what? So what does that tell me about my concavity? Yes, but what does that tell me? It didn't tell me it's constant. It is constant, but what it's telling me is what's happening there. The second derivative is always 2. Is there a place where it could equal 0? Can y double prime equal 0? Not possible. So since it's always positive, what does it tell me my graph looks like? Since it's always positive, it tells me my entire graph is concave up. That's all it tells me. All right, here's another example. Determine the concavity of this function on the interval 0 to 2 pi. What is that graph going to look like? And then do what with it? You think up? Remember, if it's outside the function, it does what? Horizontal or vertical? If it's outside, it's vertical. This is a vertical shift up 3 spaces. So this graph from 0 to 2 pi, so we have pi over 2, pi, 3 pi over 2, 2 pi. And it's bounded at +1 and -1. So this original graph, well, I need more room than this. So let's look at the sine function. What does the sine function look like? At 0, what is sine? 0. At pi over 2, 1. At pi, it's 0. At 3 pi over 2, it's -1. at 2 pi 0. So the sine function looks like this. That's just the sine. Now we have to go up 3 spaces. So our intercept here, 1, 2, 3, goes up to this. So this is our new x-axis. So at 0, then at pi over 2, it becomes 4 because 1 plus 3 is 4. Then it's 0. Then negative 1 plus 3 is 2. And then back to 2 pi. So our graph looks like this. It's shifted up 3 spaces. Okay, so now we know what it looks like. Is that an important concept you have to know? Not really. It's just good to see what it looks like. But you don't have to waste time doing the graph. Because what's the first thing we have to do to find out about concavity? Which one? I have to find the second derivative. So our first derivative, so our equation is 3 plus sine x. So our first derivative will be what? Cosine. Because derivative of 3 is 0, derivative of sine is cosine. How do you memorize the trig functions, the derivatives of trig functions? Where you shouldn't have to memorize it. I showed you all something when we first talked about trig functions and derivatives of trigs. What's the easiest thing to memorize? The unit circle. At each of these points, what's the point of this location? 1, 0. This one is 0, 1. This is 0 or negative 1, 0. This is 0, negative 1. Every point is made up of a cosine and a sine. So since this is the y value, it's sine x. This is the ones on the x. This is cosine. This is negative sine. This is negative cosine. Because the rest are 0. The x is 0, so there's no cosine. The y is 0, no sine. So that's what's the derivatives go in this direction. So the derivative of sine is cosine. So what's the derivative of cosine? Negative sine. That tells us our concavity. So let's look at this. When x is 0, it's 0. When x is pi over 2, what is my second derivative? Negative 1. Because it is 1, but since it's a negative coefficient, then at pi, it goes back to 0. At 3 pi over 2, at 3 pi over 2, it's negative 1. So this becomes 1. Or actually, to be honest with you, well, it's a sine function. And then at 2 pi, it becomes 0 again. So from 0 to pi, the second derivative is negative in the entire place. So what does that tell me is going to happen to the curve? If the second derivative is negative, what is it? Yeah, from here to here, it's concave down. That means it looks like this. That's concave down. From pi to 2 pi, they're all positive. So from here, it's concave up. And in the whole domain, we have 0 at pi. So we have concave down when x is between 0 and pi. And we have concave up from pi to 2 pi. And that's exactly what the graph looks like. So from 0 to pi, it's concave down. And from pi to 2 pi, it's concave up. So now look at these last two examples. Examples gave us functions where we can find the second derivative equal to 0. So in the first example, we had this one, where from negative infinity to 0, it's concave down. And then from 0 to infinity, it's concave up. From 0 to pi, it's concave down. And then from pi to 2 pi, it's concave up. What's important is where the second derivative is equal to 0. Because at second derivative when equals 0, is it concave up or is it concave down? Is it positive or negative? concave up nor down. It's the same in the first derivative. If we set it equal to 0, the function is neither increasing nor decreasing. When the first derivative equals 0. Since it's neither increasing nor decreasing, we call that an extrema. That's in the first derivative. But in the second derivative test, wherever the second derivative equals 0, this is called the point of inflection. The definition is this. A point C f of C where the graph of a function has a tangent line and where the concavity changes is called a point of inflection, which is just called, I call it POI. A point C, f of C, where the second derivative, okay, why is this important? Why does it say it has to have a tangent line? Where do we find the tangent line? The first derivative, because it's the point on a curve, only one point on a curve. That tells us the slope of the line tangent to it. So if the first derivative exists, then the second derivative exists. Wherever that equals 0, that's called the point of inflection. If you notice what it does, it changes the direction of concavity. It used to be concave down. There's a point of inflection. Now it's concave up. Concave down, at this point is the point of inflection. Then it goes concave up. Similar to what we did in the first derivative test. If it's positive, that means it goes, if it's a maximum, it goes positive, 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 then 0, then negative. If it's a minimum, then it goes negative, 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 0, then positive. Example 3. Determine the concavity and find the inflection point of the following. f of x equals x cubed minus 3x squared plus 2. You notice I said inflection point. That's the point of inflection. So what's the first thing you have to do? Just the derivative? Let's find the second derivative. Because concavity deals with the second derivative. So our first derivative is going to be what? 3x squared 6x. Second derivative is going to give us 6x minus 6. So before we start talking about where it's concave up, concave down, so no. Before discussing concave up or down, we must first find the second derivative, then set it equals 0 and solve. For the point of inflection. Because once you find the point of inflection, then you know that it's going to have to be increasing or decreasing on one side and increasing, decreasing on the other side. So before discussing where it's concave up or concave down, we got to find the second derivative, set it equals 0, solve for x. So we have 6x minus 6 equals 0, 6x equals 6, x equals 1. So this is my point of inflection. If we were to graph it, put it back inside our original function. That's 1 minus 3 plus 2. It makes it 0. So our point of inflection has that point there. It's at 1, 0. Without seeing to do anything else, where is it concave up? Where is it concave down? How do you test for concavity? No, not 0. Here's the point of inflection. This is where the second derivative equals 0. So pick a number to the left of it. Plug that in the second derivative. We get negative 6. So it's concave down. That means the graph on this side has to look something like this. Then pick a point on the right-hand side. Plug that in the second derivative. So we have 6 times 2 minus 6. 12 minus 6 is positive 6. It's positive, so it's concave up. The graphic's something like this. Can you tell me where the vertices are? Okay, so concave down from negative infinity to positive 1. It's concave up from 1 to positive infinity. That's where it's concave. That's the domain of concavity. How would I find the extrema points? Set the first derivative equal to 0. First derivative is 3x squared minus 6x. This is my first derivative. Set it equal to 0. We can factor out a 3x. Give me x minus 2. Set them equal to 0. X equals 0 and x equals 2. These are the points where I'm going to have my vertices. So at 1, second derivative is 0. We have a point of inflection there. At x equals 0, how do we find the point of the graph there? Plug those into our original function. And so our original function was 3x squared minus 6x. No, it's 3x cubed minus 3x squared. So our function is x cubed minus 3x squared plus 2. So when x is 0, we have 2. When x is 2, we have 2 cubed minus 3 times 2 squared plus 2. 8 minus 12 plus 2 makes it negative 2. So it looks something like this. And then we find the other intercepts and we're done. We find the intercepts from the original function. Example 4. Find the point of inflection of this function. How do we find the point of inflection? Second derivative and do what with it? Right. Second derivative, POI is the second derivative, set it equal to 0. So take the derivative. First derivative is going to give me what? Help you. I'll do the 5/3. Subtract 1, which is 3/3, makes it 2/3. This is the same as 3/3. So 5 minus 3 is 2/3. Then the second derivative, we have 5/3 times 2/3, and subtract 1 again, which is 3/3, makes it negative 1/3. So we have 10/9 x to the power 1/3. What does that tell us? This is the second derivative. Where is it equal 0? Right. Because the only way a fraction equals 0 is if the top is equal to 0. So this gives us a new modified definition of the point of inflection. What x can we not use here? Very good. What x can we not use? X cannot equal 0. So what this tells us, our point of inflection is at x equals 0. Which now brings us to our actual formal description. Occurs when 1 whatever x makes that equal 0. Whatever x value makes the second derivative undefined. Which is the vertical asymptote of the second derivative. So whenever you're asked to find point of inflection, if you can't set it equals 0, if it doesn't exist, then look where it makes it undefined. Those x values will be the points of inflection. Can you have more than one point of inflection? Oh. Well, it's so far we're looking at cubic functions. If you look at it this way, 1. I said the maximum number of vertices is equal to what? N minus 1. Is the degree of the polynomial. The degree is the highest exponent. So n minus 1 is the number of vertices you'll have. The maximum number of point of inflections is equal to the number of vertices minus 1. So basically, you can look at it n minus 2. Example 5. Find the point of inflection of f of x equals x to the fourth. So what do you have to do first? So the second derivative is equal to 12x squared. So in other words, that tells me it's going to be positive everywhere. Can't ever be negative? No, because it's squared. Any x you put in there, you square it because it's positive. So it's always positive, always greater than 0, which means it's always concave up. Even though I could take the second derivative, set it equal to 0. That's my point of inflection. The graph looks like this pretty much. The next example. Okay, y equals x to the power 1/3. Or I could have given you this equation as cube root of x. I should have given you that and seen how you solved it. Because you have to find the second, its question is asking, find the point of inflection. So we take the first derivative, which gives us what? 1/3 x to the power negative 2/3. How did I get negative 2/3? Yeah, when you take a derivative, you bring down the power and subtract 1, which is 3/3. 1 minus 3 is negative 2/3. Second derivative, keep on doing the same thing. So we have 1/3 times negative 2/3 and subtract 1, which is 3/3, makes it negative 5/3. Negative 2/9 x to the negative 5/3. Which makes it negative 2/9 x to the 5/3. Negative 2/9 x to the power 2/3. Again, this is all algebra. You should know how to do this already. It's all algebra. Rules of exponents. So can it equal 0? No, because you can't make it can't equal 0 if the top can't be 0. Can it be undefined? Yes. Undefined at x equals 0. So when x is on the bottom and goes to 0, it's a vertical asymptote, which gives us a vertical tangent line because it's an asymptote. The graph of this function would look like this. Right inside here, the curve actually is a lot steeper. It's a lot steeper in there. It goes. The bigger your denominator of your radical, the more steep it becomes. So what we have here is that's a vertical tangent line. So x equals 0 is my point of inflection. Next example. Example 7. A particle moving along a horizontal coordinate, okay? A particle moving along a horizontal coordinate plane or line positive to the right with the function. This is SF, since we're talking about a moving particle, as 2t cubed minus 14t squared plus 12t minus 5 for all t greater than 0. Find the acceleration and the velocity and describe the motion of the particle. So let's find the velocity first. How do we find the velocity? How do we find the velocity? Anybody? Of what? It's the first derivative of our position function, which will give us 6t squared minus 28t plus 12. And t is still positive. Okay, what can you tell me about that? What can I do with that? Remember, you're supposed to describe the motion. We found the velocity. Great, no problem. But what does it tell us? Well, time is always positive, so it can't go backwards. Or can it? It can't go backwards. I say no. But the velocity can be positive or negative, which means accelerating or slowing down. How do we find this? What do we have to do now? Set it equal to 0. Set it equal to 0. And then solve for t. I can divide everybody by 2. Divide everybody by 2. Now I can try to factor it. Put whatever the first term is in. The second sign's a plus, which tells me the signs are the same. And they're both going to be the first sign. They're both going, in this case, they'll both be minus. Take the first and last terms. 3 times 6 is 18. Now we got to find out what times what equals 18. When we add them together, we get the middle term. We get 14. It won't be an integer. So we got to use what? We can't use factoring. It won't be integers. Let's see. Hold it. 11. What?
3t times 4.2 got to be 9t squared.
Wait, I'll show you a new way. There's more than way. The way you guys were taught in high school and college and earlier was horrible. This method here for factoring is a lot easier. Well, I'll show you what I'm sorry what I'm talking about. No, I'll come back to this one in a second. Show you how to use this method. It's much better because if what a lot of teachers tell you, well, if you can't factor it, if no, it's much more difficult. No. So since we can't do this, we have to use Pythagorean theorem. So I'll plug in my values. I got negative of negative 14. Negative 14 squared minus 4 times 3 times 6 over 2 times 3. 14 plus or minus 16, 4, 5, 4, 1, 196. 18 times 4 is 72 over 6. 14, 196 minus 72 is 124. Correct so far. So 6, 18. Mm, 96. Oh, it's 122. 122. Okay. 124 breaks down to 2 and 62, 2 and 31. So we have 14 plus or minus 2 square root of 31 over 6. Factor out of 2. The 2 and the 6 cancel. So those are my two x values. And this is just for my x-intercept. They would not give me something like that if it was not factorable. So we have 18. Let's try 672. 72. 9 and 8. Let me see, make sure my numbers are correct. 2t cubed, so it's 6t squared minus 18t plus 12. I can factor out of 2. $18 and then 2 and 3 6 and 3 There's a mistake. It was 22. So this would be 11. Okay, now we go back. Then we can go back and factor this one. I'll show you how this one's going to work. That one should have been a 22 here, not a 12. Yeah, 22t. So back to this case here. We have, because even this will give us a weird number. So we have 3t squared minus 14 plus 11. Remember, we divided by 2. That 2 has to come back at the end. Yeah. Equals 0. So 3t, 3t, they're both the same. They're both minus. What times these two gives me 33? What times what gives me 33? What times what equals 33? That when I add them together, I get 14. 11 and 3. So it doesn't matter since they're both the same. Now, the next step is factor out do what you can out of these. This will get rid of that question you had earlier. I can factor out a 3 there. Erase it. There's my factor. Whenever you have a non-1 leading coefficient, just put it down. It'll factor out at the end. So solving each one of these will give us 3t equals 11. T is 11 over 3. T equals 1. So these are my intervals of where it's my velocity. So my intervals. This is 1. This is 11 over 3. My intervals are from negative infinity to 1, from 1 to 11 third, and then 11 third to infinity. Remember, my velocity formula is 3t minus 11t minus 1. So I pick a number in this domain. I pick 0. And I plug it inside there. Two times negative 11 times negative 1 is positive 22, so it's positive. So it's increasing. The function is increasing all the way from negative infinity to positive 1. Now between 1 and 11/3, this is 3 2/3. I pick 2. Three times 2 minus 11 times 2 minus 1. 6 minus 11, 2 minus 1. Negative 5 makes it negative 10, so it's decreasing. In the middle interval, the function is decreasing. And then the next one, I use a 4. So the velocity at 4, 2, 3 times 4 minus 11, 4 minus 1, 12 minus 11, 3. So it's positive, so it's increasing. So the function is increasing here, decreasing here, and increasing there. That's the velocity. So it's accelerating. I mean, it's increasing its velocity, it's decreasing its velocity, and but as you said earlier, it's when you have a velocity that's decreasing, it's negative. So this one moves to the right because it's positive. This one moves to the left since it's the velocity is negative, it's going backwards. And this one moves to the right. So this object moves to the right, moves back for a little bit, and then moves back to the right. So we have here, we have our original function, s of t equals 2t cubed minus 14t squared minus 22t minus 5. We found our velocity function, which was 6t squared minus 28t minus 22, and t is still going forward. Now we're going to find the acceleration. 12t minus 28. Set that equal to 0. So we have 12t equals 28. T is equal to 28 over 12. They both have a 2 in common. They both have a 2 in common. So my function equals 0 at 7 over 3. Seven over 3 is 2 1/3. So I can use 0 here, and I can use 3 here. So I have to pick my test points. Plug those into my acceleration. 12 times 0 minus 28 equals negative 28. A at 3. 12 times 3 minus 28. 36 minus 28 is 8. So this says it's concave down. This is concave up. So what's really happening in this interval here? From negative infinity to 7/3. Acceleration's it's going down. It's decelerating. What happens at 7/3? It changes direction. The acceleration changes. Because now from this one, from 7/3 to positive infinity, it begins to accelerate again. Example 8. Sketch the graph of this function. It has 5 things, says using these steps. Identify the extrema. Find where f of x increases and decreases. Where f of x is concave up and down. Sketch the graph. Plot some points. All right, what do we know about this graph already? Just by looking at the function, what do we know about it? What does that mean? It means it's an even function. Or how did you find that out? Yes, so the leading coefficient, x fourth. The degree is 4. What does that tell us? And the leading coefficient which is greater than 0. So what do both of these together tell us? Because the leading coefficient is positive, it tells us at the end behavior, it goes up. And what does this tell us? Since the degree is even, that means both direction point the same direction. Both ends point the same direction. If the degree is even, then both ends point the same direction. And since it's positive, they both point up. We know that. How many x-intercepts will we have at most? The maximum number of solutions. We'll have 4. So at most we'll have 4. Somewhere we'll have 4 x-intercepts. At most. We can have 3, we can have 2, we can even have 1. Can we have 0? Yes, because it's an even degree. You can't have no real solutions. So now we have identified the extrema. How do we identify the extrema? Actually, what else do we know? We know the y-intercept is 10. We know it has to cross through 10. That's the only thing we know, and we know the end behavior has to be the same. The extrema. How do we find extrema? Yeah, take the first derivative, set it equal to 0. So since our function is x to the 4th minus 4x cubed plus 10, our first derivative is 4x cubed minus 12x squared. Set that equal to 0. So we can factor out a 4x squared, x minus 3. Find our zeros. Take this equation and this equation, set them equal to 0. So the extrema occur at 0 and at 3. Our extrema, when x is 0, plug it back into our original function, we get 10. So we know we have 1 point there. When x is 3, we get f of 3, 3 to the 4th minus 4, 3 cubed plus 10. 81 minus 4 times 27. 10 plus 81 is 91 minus 4 times 27 is 108. 108 minus, it should be negative, is negative 17. So at negative 3, the maximum or the minimum is going to be at negative 17. So we found the extrema. Where is it increasing? Where is it decreasing? So to find out where it's increasing, let's pick a number that's to the left of our extrema. So here's our first derivatives. We're at 0 and 3. If I put -1 inside my function, my first derivative would be 4 -1 cubed minus 12 -1 squared. So it's -4 minus 12 equals -16. So my slope to my left of 10 is going down. So it's got to be going down to this one. What happens between 0 and 3? Let's pick 1. So we have 4 times 1 minus 12 times 1. 4 minus 12 is -8. So it still keeps on going down. So it has to be going down to this point. And then at 4, we have 4 times 4 cubed, 12, 4 squared. 16 is 64 minus times 16. 256. 12 times 16 is 192. Is 64. So it goes up. So we know the graph looks something like this. Where are the points of concavity? So since the first derivative was 4x cubed minus 12x squared, the second derivative is equal to 12x squared minus 24x. Set that equal to 0. So we factor out 12x. $12x equals 0 when x is 0. X minus 2 equals 0 at x equals 2. So my point of inflections happen at 0 and 2. So my second derivative at 0 and 2, what happens there? These are my POIs. So I take -1, 1, and 3. So my second derivative at -1 is 12 times -1, -1 minus 2. -12 times -3 is positive 36. So on this side, it's concave up. So under the graph will look like this. At 1, 12 times 1, 1 minus 2 is -12. So this between 0 and 2, it's got to be going down. It looks something like that. And then on the other side, 12 times 3, 3 minus 2, it's going to be positive. So on this side, it's got to start being concave up. So it's got a concavity point at 2 and 0. We just don't know where the actual x-intercepts are. So it's got a concave up, concave down, and then concave back up. Something like that. Let's look at Desmos. X to the fourth y equal x to the fourth. Oops. Minus 4x cubed plus 10. Remember, we have a 0 there. We have the lowest point at negative 17 at 3. So it crosses between 1 and 2 and at pretty close to 4. So that's what the graph's going to look like. Again, we don't need calculators because we can do it on our papers. Let's see if there is another one. Ooh, a rational one. F of x equals x plus 1 squared, 1 plus x squared. And it's going to find the same, ask us to find the same things. Now, the hard part about this, okay, what can this tell us? Where are our x-intercepts? Where are do we have any vertices? What's our horizontal and vertical asymptotes? What can you tell me about this equation? Just by looking at it. What's my y-intercept? The y-intercept is at 1. No. How do you find the y-intercept? Set x equal to 0. So we have 1 squared is 1 over 1 is 1. That's the y-intercept is at y equals 1. Do we have a vertical asymptote? How do you find vertical asymptotes? At the bottom equal to 0. So we have no vertical asymptotes in the real realm. Do we have any horizontal asymptotes? Horizontal asymptote occurs at 1. The numerator exponent is 2, and the denominator exponent is 2. Since they're both the same, it's simply the coefficients, which is 1/1, which is 1. So the line y equals 1 is a horizontal asymptote. So let's look at the first derivative. See where it's increasing, where it's decreasing. Do I have any restrictions on my domain? Why not? And can never be 0, correct. Since the denominator can never be 0, we have no limitations. Our domain is from negative infinity to positive infinity. So what's our first derivative? How would you find the first derivative? What kind of equation is this? It's a quotient. Oh, we get what time here? 10:40, 9:40, or what time? 9:50? Okay, good. We have 7 minutes. So we have f of x over g of x. We have to use a quotient rule, of course. So the top is x plus 1 squared. The bottom is 1 plus x squared. The derivative of the top is 2x plus 1 times the derivative of the inside is 1. So it's 2x plus 1. And the other one, derivative is 2x. So we have 2 times x plus 1 times 1 plus x squared minus 2x x plus 1 squared all over the denominator squared. Okay. So let's combine all the bottoms. Let's fix the numerator. So we have this will be 2x plus 2 times that. So we got to FOIL the top. 2x times 1 is 2x. 2x times x squared is 2x cubed. Then 2 times 1 is 2x squared. This one is going to be x plus 1 times x plus 1, which makes it x squared plus 2x plus 1 times 2x, which makes it 2x cubed plus 4x squared plus 2x. Leave the bottom alone. I hope you all don't just watch me do it. Try to do it yourself. Because this is just basic algebra. The calculus is finished already. Now it's just algebra, the difference quotient type stuff. Who's lost already? Because if you're spending your time just copying, then you're lost. Combine like terms. So I have 2x cubed plus 2x squared plus 2x plus 2. 2x cubed minus 4x squared plus 2x. I can remove the parentheses now. Distribute the negative. Combine like terms. So 2x cubes cancel. 2x squared, 4x squared is 6x squared. Positive 2x minus 2x cancels. Plus 2. 1 plus x squared squared. So 1 plus x squared, 2 times 1 is 2x plus 2 times 1 plus x squared. So 2x cubed, 2 plus 2x squared. And I have here x plus 1 squared, which is x squared plus 2x plus 1 times 2x, 2x cubed, 4x plus 2x. Combine. Minus that. It should be plus. So that should be minus. So we should have 2x cubes cancel. So we should have negative 2x squared plus 2, which should give me negative 2x squared plus 1, x squared plus 1 squared. What's minus? Minus. So this is my first derivative. All right. Again, the denominator can never be 0, so we have no asymptotes. The only way we can have a 0 is if the top is 0. So we have x squared minus 1 equals 0. So x squared equals 1. X equals plus or minus 1. So we have vertices at x plus or minus 1. So we have vertices at plus or minus 1. We have a horizontal asymptote at 1. So there's going to be a vertex here, a vertex here. So looking at my first derivative test. So at -2, 0, and 2, what happens there? Is it going to be increasing, decreasing? Where our function is -2 x squared minus 1, x squared plus 1 squared. When x is -2, we get a +4 minus 3, so it's -6 over That's gonna be a positive, so it's gonna be negative, so it's gonna be decreasing here. At 0, we have -2 times -1 over 1, which makes it 2, so it makes it increasing. And f of 2, -2, 4 minus 1 is 3, 4 plus 5, 25. So it should be negative, and it's going to be decreasing. So it's going to be decreasing, increasing, and decreasing. So at -1, in our original function, we got -1 plus 1 squared, 1 plus -1 squared is at 0. So we got a vertex there at 0. At 1, we have 1 plus 1 is 2 squared, 1 plus 1 squared. So it's 4 over 2. So our graph will look something like this. Now we test the concavity. We'll see this is concave up. Here's the point of inflection. So we'll have from -infinity to 0, it's concave up. It's going to be positive. And then from 0 to positive infinity, it'll be concave down. We'll do the last 2 examples next time and then move on to the next section. Took a little bit longer than I expected. Again, if your algebra skill is not up to par, you should be